Good morning, everyone. Thanks very much for coming to the Berkeley Lab Earth Sciences Division Distinguished Scientist Seminar. This seminar series is a monthly seminar featuring eminent individuals from various disciplines in the scientific community whose research is outstanding, interdisciplinary, and of broad interest to the strategic interest initiatives in earth sciences. And today is our great pleasure to have Dr. Bob Enick as our speaker. Bob has been a professor of chemical and petroleum engineering at the University of Pittsburgh since 1985. And he has also been a fellow with NETL since 1987. Bob is an expert in the fields of enhanced oil recovery, geological carbon sequestration, hydraulic fracturing, and high-pressure phase behavior and viscometry. His work has been widely published, and in 2002, he was given the Presidential Green Chemistry Challenge Award, and Bob was also the winner of the 2011 U.S. Secretary of Energy's Achievement Honor Award. Without further ado, please join me to welcome Professor Bob Enick.
Thank you very much. Thank you for the invitation. It's great to be here. Thank you for taking time out of your day to be here. So I'd love to spend the next hour telling you about the high-pressure world that I live in. It's a good kind of high pressure. Mainly, most of my work deals with CO2 enhanced oil recovery, and perhaps as we go through this talk, you might see some possible applications to the fine work in sequestration that goes on here. So another title that you might envision for this talk, at least the way that I think about it, is this, is what in the world can you do with chemistry and chemical engineering as applied to petroleum engineering? And I found out from being in a department that has both of them that the answer is actually quite a bit. When I first started in my career, there's a lot of people that sort of said, petroleum engineering, that's not a very exciting place or a very challenging place. Chemistry and chemical engineering is a lot more fun, but actually there's a great amount of excellent work that goes on in petroleum engineering, and they can benefit from a lot of chemistry and chemical engineering and physics. And I think the interface between the two is really an exciting place to be working at. You know that when you would drill a well in the United States, most people are hoping to strike a few things, right? You're hoping to strike oil. Here in Pennsylvania, where I'm from, we're in the middle of the Marcellus Shale region, so people are hoping that they have natural gas under there, or you might drill wells for water. But there are a few places in the United States that have not just reservoirs of natural CO2, but prolific reservoirs of natural CO2. In fact, in the world, the United States and North America in general has this uncharacteristically large amount of natural CO2. Most of the reservoirs are surprisingly high in purity. Some of them, such as in LaBarge, are very low purity, but utterly massive in the amount. And because of that, there's a great amount of interest of what to do with all that CO2. Well, in the United States, we also have a large amount of crude oil. We've been working fields containing underground layers of sandstone or carbonate for decades, primarily in places like West Texas and in the Permian Basin, where there are several thousand feet below the ground, a great deal of crude oil reserves. And the first way that you try to get this out is by the natural pressure, just from the pressure of the formation and some of the gas that's dissolved in the oil. When you depressurize at the production wells, you get the natural forces to produce it. And then after that, you can inject water into these formations. And this can go on for decades, 10, 20, 30, 40, 50 years of water flooding. But even after all those decades of primary and secondary recovery, usually much more than half the oil remains in place. And here you see a schematic from this company that shows water coming down into this underground layer of sandstone, being injected into an injection well, and proceeding to push and displace the oil towards these 4 production wells around it. So why is so much left behind? Why is there such a profound amount of oil where we know exactly where it is, but it's still there? Why is such a poor job done by primary and secondary flooding even after all of these years? And that's basically because water and oil don't mix very well. It's not a high-tech explanation, but it's actually very accurate. If you take crude oil and brine, mix them together, you'll get a nice sharp interface between the two of them, and it's just not a very good solvent. It's not really that different from having a lot of oil in your shirt and trying to get it out with water. You're going to leave a lot behind. And the capillary forces retain a great deal of the oil in the small pores of the rock. CO2, on the other hand, is a really good solvent. It's not a perfect solvent, but CO2 is a very good solvent for oil. So let me just take one moment, if you've never seen or aren't familiar with a pressure versus composition diagram, and this is at one temperature, which would be the reservoir pressure. So let's say, just for example, that we have a mixture that's 50-50 of oil, which is on this axis, and CO2 here. And let's say that we're at a pressure corresponding to this value right here. This is a one-phase region. So at those conditions, that's a fair degree of miscibility between the two. In fact, this whole region right here is a single-phase region. This pressure usually is the highest pressure your equipment can go to in the lab. For instance, in my lab, we take these diagrams up to 10,000 psi. Over here, when you get higher proportions of CO2, relatively smaller amounts of oil, you have this two-phase liquid-liquid immiscibility gap. So it's not that they're completely miscible, but it's much, much, much more miscible than water. What's really fascinating is even though they're not miscible, in the porous rock they can become miscible. Because what happens is, if you inject CO2, and on this ternary diagram, the injected fluid is here at this part of the triangle, and here we have heavy hydrocarbons and lighter hydrocarbons. And this is a very simplistic model, but it actually represents what happens very well. Your reservoir oil is a mixture of heavy hydrocarbons and lighter hydrocarbons. You may think of this as C1 up to C25 or C30, and this is C30 and higher. So here's the reservoir oil. Here's the CO2 that you're injecting. This diagram is at one temperature and one pressure. So you see that if you mix the two, if the CO2 mixes with the oil, the mixture is somewhere on this line. And there's this huge two-phase region here. So once again, it appears like it's not going to mix. It's going to be immiscible. But what happens is, if you enter, this is like being back in your sophomore year of thermo. If you're in the two-phase region, this is a tie line. This is the CO2-rich phase, and this is the oil-rich phase. And now you see the CO2-rich phase has a slightly different composition. It's not pure CO2 anymore, but it's following this path. And then this mixes with the oil, and the mixture might be on this tie line. And it splits into two phases, and this is the CO2-rich composition. So you see what happens is the CO2 comes into the reservoir. It, in essence, extracts the lighter hydrocarbons from the oil near the injection well, and that mixture becomes miscible with the reservoir oil. This is the one-phase region. And that's why CO2 flooding is so very popular, because it actually can develop complete miscibility and, in essence, recover 100% of the oil. So what happens? Here in the United States, we have these massive supplies of CO2, and then we have these massive amount of fields that have oil, and we know the oil is there. And when you put the two of them together, you get a CO2 enhanced oil recovery industry that's currently thriving and doing very well. The arrows that are pointing up on this diagram are sources of CO2. And you see these dark arrows? These are natural sources. This is where they drill wells into natural formations, and they get high purity natural CO2. Actually, the largest one of these sources is located in Wyoming. It's in one of the messiest gas mixtures you'd ever want to see. Only about 20 or 30% methane, 20 or 30% CO2, 20 or 30% H2S, nitrogen, helium. It's a quagmire of gases, but it's absolutely prolific. There's literally centuries worth of CO2 there for enhanced oil recovery at that processing facility. There are also, especially in West Texas, large sources Now, it's called anthropogenic CO2, but just to make it clear, this is actually CO2 from underground reservoir. So it's actually made by nature, but it's in a methane-rich fluid. So they process natural gas to sell methane, and CO2 is a byproduct. And they used to vent the CO2, but some of these gas plants actually now sell it into pipelines. Over here, this is one of the most prosperous areas of the country right now, and growing areas for CO2 enhanced oil recovery. You have the Jackson Dome supply of CO2, supplying CO2 enhanced oil recovery fields in the southeastern part of the United States. So the arrows pointing up are the sources. The arrows pointing down are the places where enhanced oil recovery occurs. This is the Permian Basin. This is where most of the action is. And there are just a few places where CO2 is currently made during the manufacture of a product, such as ethanol here or fertilizer here. And that's currently a teeny tiny portion of the CO2 used for enhanced oil recovery. Obviously, if CO2 sequestration occurs and is legislated, that could become a much larger proportion. Typically, you're told not to put up a lot of text on slides, but you have to violate it once in a while. And some of these numbers, I think, are really important to gain a perspective of this. Of the 7.6 million barrels of oil produced in this country, about 4% of it, or 285,000, comes from CO2 enhanced oil recovery. 3 billion standard cubic feet of CO2 are injected into the ground every day. About 11,000 standard cubic feet of CO2 are injected to produce a barrel of oil. If you burn a barrel of oil, it releases 8,000 standard cubic feet. Another way to think about it, 175,000 tons of CO2. This is the one that really gets everyone's attention. It actually takes 4 or 5 barrels of liquid CO2 to get 1 barrel of oil out. And believe me, the oil companies don't like this. You know, they don't want to use 11,000 standard cubic feet to get out 1 oil. Right now, some of them promote that because it makes it look like, well, it is. It actually sequesters more CO2 because you're injecting this many to get out a barrel that releases this many. But believe me, they would like this number to be much, much, much smaller. It's a lot of CO2. There's over 3,000 miles of CO2 pipelines in this country. And only 15% of the oil in place is recovered by this process. Coal-fired power plants, they emit roughly 30 times as much CO2 as is used by all the CO2 for enhanced oil recovery. And yet only an incredibly small fraction of truly anthropogenic CO2 is used for EOR. And one of the reasons is right at the bottom. When they purchase CO2 from these natural sources, they're paying roughly $15 to $20 a ton for the CO2. The price of CO2 is actually contractually tied to the price of oil. So when the price of oil drops, the price of CO2 drops. When the price of oil goes up, the price of CO2 goes up. But they're paying roughly $15 to $20 a ton. What's the cost of capturing CO2 from the best CO2 capture things? This is disputed. You'll hear all sorts of different numbers, but I think it's roughly 4 to 5 times as much. Sorry, 4 to 5 times as much. So there's no economic incentive to purchase CO2 captured from a power plant because it would cost $70, $80 a ton, and they can get CO2 for $15 to $20 a ton. So that's a challenge for CO2 capture. So CO2 is doing so well. If there's this big infrastructure with all these sources and nearly 300,000 barrels of oil a day and all of these jobs, then what's the problem? There's a profound problem. Almost every one of these CO2 enhanced oil recovery fields has major problems getting oil out of the ground. Even though they're economic, they want to be, and they can be, much, much, much more economic. And this is the primary killer for enhanced oil recovery. The viscosity of CO2 in centipoise, which is the same as millipascal seconds, is roughly 0.05 at enhanced oil recovery conditions. This is temperature. These are lines of constant pressure. This is about EOR. That means that CO2 is roughly 20 times thinner than water. And oil viscosity in fields where CO2 is applied ranges from 0.5 to about 5 or 6 centipoise. That means the CO2 is 10 to 100 times thinner than the oil being recovered. And that leads to profound and prolific problems. So the low viscosity of CO2 increases the mobility ratio. You know, it's said every slide run that equation, you lose half the audience, right? I think this is my only equation. So please don't be discouraged. And the half of you that just drifted off, please hang in there. So the mobility ratio looks like this. This is the viscosity of CO2. This is the viscosity of oil. Upstairs, we have the relative permeability of CO2. If you're not familiar with that term, all that it is a measure of how easy it is for the fluid to move through the rock. Okay? Downstairs, we have the relative permeability of oil. We want the CO2 to be less mobile than the oil. So we want this mobility ratio to be 1 or less. We want it to be small. So back to grade school. How do you make this small? Well, you could make the numerator small, or you could make this denominator big, or you could make this entire thing small. And that's all that it comes down to. The most profound challenges facing CO2 enhanced oil recovery is, can you make the relative permeability smaller? Can you make the viscosity of CO2 bigger? Or can you make this entire term, lump term, smaller? There's not too much you can do about this because the oil's down there in the rock. So you're not going to make much progress attacking that. So now let's pretend we're in a helicopter. We're flying over West Texas. And there are a bunch of wells in this beautiful pattern that's called a 5-spot pattern. The arrows pointing down are where they inject CO2. The arrows pointing up are where they produce CO2, oil, and brine. So this is the 5-spot pattern, and what we are particularly interested in is the repeating representative unit of that 5-spot. So in essence, this is a symmetric little pattern. And on this diagram, which is about 50 years old, but still conveys the message beautifully, this is the problem. Again, we're viewing from above. This is about what happens in most fields right now that you do CO2 enhanced oil recovery. Here's the injection well, where they're injecting CO2. This is that representative pattern. So this is the production well. And the CO2 fingers through. This is a snapshot of where the CO2 has progressed when it first breaks through or when it first starts to flow into the production well. This is a mobility ratio of 71. That means the CO2 is roughly 70 times less viscous than the oil, which is a number that occurs in oil fields today. So do you see this gray area? CO2 is doing a great job getting the oil from that gray area. It's a good solvent because it develops miscibility. The problem is that it hasn't even touched these white areas. So what they need to do is they will start taking the CO2 that comes out, they'll re-inject it with new CO2, and they'll just continue to flood this for decades and decades and decades. 10, 20, 30, 40, 50 years. Now, if we could make the CO2 less mobile, if we could make it thicker and get the oil and the viscosity of CO2 to be the same, then this is how the CO2 would flow through the sandstone or through the carbonate rock. Do you see how smooth and uniform it is? It's just marching through the formation and sweeping it out. If you could go from here to here, it would have an absolutely dramatic, profound, transformational effect on this. So how can we do that? How can we do that? Well, here's the state-of-the-art solution. Let's take a look at the top. We have the relative permeability of CO2. This is how it's done in 90% of the oil fields right now. This is a plot of relative permeability versus CO2 saturation. It's not the saturation you're usually familiar with. This saturation term means a volume fraction in the pores of the rock. So if you have more and more water in the rock pores and less CO2, then let's say that we move to this value here where it's 50-50. Half the pores are half filled with water, half filled with CO2. Look at the relative permeability of CO2. It has gone from a value up here all the way down here. And what about the water? If you had nothing but water in the pores, its value permeability would be here, but it goes way down like this. This simple figure is the fundamental reason why in 90% of those oil CO2 floods that go on, they inject roughly the same volume of CO2 and water. They alternately inject CO2 and water. They'll inject CO2 for a month, and then they'll put in water for a month. CO2 for a month and water for a month. And what are they doing? They're just beating down the relative permeability. But what's the price you pay? You're injecting all this stinking water. And they don't want to be injecting water into these wells. They want to be injecting the good solvent. And so you're injecting water, you're producing water. It's a nightmare of an operational problem, but it's the best idea they have. So I don't know who has more acronyms, government facilities or the oil industry. It's a really close competition. So what I know about the oil industry, the acronyms are much less accurate. For instance, they call this WAG. So it's water, but it's never water. It's always brine. They never do this with fresh water. And they inject it alternately with gas. It's really not gas. It's supercritical CO2. But WAG just sounds so cool that it's called the WAG process. So everybody loves WAG. WAG is the way to go. It makes things profitable. The Republicans love it because it produces oil, generates jobs, and the president loves it because it sequesters CO2, even though most of it is natural. Well, we'll forget about that for a while. But I mean, it's a clear demonstration that you could sequester CO2. So it's a great technology. It's thriving. This is the way that it's done. You inject the CO2. You inject it alternately with brine. You develop a miscible zone that pushes a lot of oil out. And coming out, you have three things. You have oil. So it goes into a big tank. You separate it by density, and you sell that. You have brine. You just recycle that and re-inject it. And then you have CO2. It's actually some other gases in there, but let's just say it's CO2. It gets recompressed and recycled with brand new CO2. That's how the process works. Even though that process works very well, economically, they make profits. It's a thriving industry. It could do so much better. It could do so much better. So after primary floods and after water flooding and even after CO2 enhanced oil recovery, CO2 flooding only gets 10 to 15% or 20% at most of the original oil in place. Even after you do primary recovery and water flooding and CO2 flooding, you still have 1/3 to 2/3 of the oil still remaining there, still sitting there in the rock. It's so frustrating. And WAG is not the ideal solution. It requires massive water management. So when you go to these oil fields, there are people whose whole lives are nothing but managing water. Water coming out of wells, they have to treat it a little bit, they have to redistribute it, re-inject it, they have to separate it in separation wells. WAG delays the injection of the solvent, right? You're injecting months of water, and the water isn't a solvent at all. And you have a whole bunch of facilities dedicated to it. This is where one of our research areas comes in. We're trying to thicken CO2. We're trying to make the CO2 just as viscous as the oil being recovered. And if we could do that, I believe that we could easily double or triple the oil production rate coming from these enhanced oil recovery projects. That is our goal, and it is really, really difficult. So what this is a picture of a thickened hydrocarbon fluid. This is napalm. Napalm was weaponized gasoline. So when napalm was invented, they tried to thicken it, and the first way they did it was with tiny molecules that self-assembled and made rod-like macromolecules in solution. And the way that it gets its name is that they used naphthenic and palmitic acids. They didn't just use those acids. They used the hydroxyaluminum alkanoates of these acids. And they took the Na and the palm from here and turned it into napalm. After that, when polymers hit their stride and were invented, you could simply take polystyrene. You could take a styrofoam cup, put it in gasoline, stir it around, heat it up a little bit, maybe to make it go more quickly, and you could thicken it. What this tells you is that there are two ways to thicken fluids. Either really, 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 really big molecules or teeny, teeny, tiny molecules that self-assemble and form these long viscosity-enhancing macromolecules. This is what we're trying to do to CO2. We're trying to make a beautiful, transparent, thermodynamically stable, viscous solution where the CO2 viscosity is the same as the oil. If you read in the literature for thickening things, we do not want to make a milky white or opaque gel. This gel is actually a bunch of micron-scale fibers interlocked with the solvent in the pores. That will not flow through a rock. This can flow through a rock. This cannot. What will happen if you inject this into a piece of sandstone or carbonate rock, the rock will filter out all these fibers. They'll just get stuck on the face of the rock, and it won't work at all. So our challenge is a little bit harder than people that make gels in vials, because we have to get whatever viscous solution or gel that we form to flow through a piece of sandstone or limestone. We had some success with polymers. Our idea was to make a polymer with a CO2-loving parts and associating parts, that if we got these polymers to go into solution, not only would they start out with a high molecular weight, but these associations with CO2 phobic groups would make a large viscosity-enhancing macromolecule, and we were successful. We made the only CO2 thickener that's been identified yet. It's a copolymer. This monomer is a fluoroacrylate. It's the most CO2-loving monomer there is. This is styrene. This doesn't like CO2, but it likes to associate through pi-pi stacking because there's a different electron density on the periphery of the benzene ring than there is in the core of the benzene ring. So they sort of stack like this. When you put this into CO2, you can adjust the CO2 viscosity to the oil viscosity with less than a weight %. But it's too expensive. Fluoroacrylates cost roughly $50 a pound. We're trying to make a thickener that costs $3, $4, $5, $6 a pound. So we then tried to make a CO2 thickener using polymers, and we weren't alone. In the early 1990s, there were a whole bunch of groups, mainly interested in chemical engineering applications, of people that were studying how CO2 interacted with different chemical functional groups to see which ones were called CO2 philic and which ones would be CO2 phobic, CO2 loving or CO2 hating. And so what people started noting, and even though this is a very simple diagram, it sort of makes the point. The carbon in CO2, even though this is a nonpolar molecule, it has a quadrupole moment. And basically what that means is that the C is a little bit positive and the oxygens are a little bit negative. So if you have a carbonyl group here, there's a lot of electrons here, right? So this oxygen's a little bit negative. It sort of likes to hang out with this C, which is a little bit positive. And those kind of Lewis acid, Lewis base interactions were shown to work. So what we started doing was making polymers, and you'll see in the following slides, we have a bunch of polymers. We spent years making polymers. Polymers of all sorts of configurations. Polymers with all sorts of oxygen. Polymers with all sorts of amines, because amines might interact with CO2. Polymers with oxygens on the side chain. Everything. It was so frustrating. Those 4 slides were about 4 years of my life, and that's why I went through them. I'm still in counseling over those. It was one of the most frustrating streaks of research that we ever did. But here on this slide, this is actually the suite of every CO2 soluble polymer that's ever been identified. So this is all of them. And you know there's a lot of polymers out there, and this is a small number. This is the fluoroacrylate, too expensive. You can't do it. This is silicone oil. This is great. $3, $4 a pound. You could buy thousands of tons of it. So that's a promising kind of a polymer. This is fluorinated ether. That's not going to work out. This is extraordinarily expensive to make. This is a sugar acetate on the side chain of a polymer. Here's amorphous polylactic acid. That dissolves in CO2. And polyvinyl acetate, polymethyl acrylate. But you have to be careful. These things are soluble, but they're not that soluble. You need tens of thousands of psi. Oil field operations are nowhere near that. When they do enhanced oil recovery, the pressures are typically 1,500 psi to about 4,500 psi. Every polymer I just showed you requires about 9 to 10,000 or more. With the exception of those expensive fluoroacrylates, all the affordable ones have pressures way, way above oil field pressures. I'm an experimentalist, and I'm sort of proud of it. And you know, I had to almost go crying to my molecular modeling friend, Carl Johnson at University of Pittsburgh, and apologize for all the cruel things I said about molecular modeling people for decades. And I just begged him for help. I said, there's got to be a CO2 soluble polymer that doesn't have fluorine in it that you could help us make. Well, Carl found out that this polymer, which no one had ever made, actually has more, modeling people also make the best slides. You know, Carl made this slide for me. He's just, I like modeling people now. This is the monomer that Carl invented that had more favorable interactions with CO2 than any other polymer that he ever modeled. So for instance, this is the monomer unit, and in each of these diagrams you could see it. It's the same monomer unit of the polymer, just tilted in different directions. And in every one of these diagrams we have a CO2. You see these CO2s right here? And basically what Carl did was he would measure the strength of the interactions and the configurations using ab initio methods, and we found out that this unfortunately wasn't as good as some of the others, and we're still not sure why. So in summary, what I'm about to show you is one slide where we identified, after 6 years of funded work, what the most CO2 soluble, CO2 loving, high-tech, fancy pants polymer that didn't contain fluorine is. And it's Elmer's glue. It's polyvinyl acetate. It's a $3.50 per pound commodity chemical, and at the end of the day, there is no high molecular weight polymer that's more soluble in CO2 than polyvinyl acetate, but you need about 10,000 psi to dissolve it. So that's way above enhanced oil recovery conditions. So having exhausted ourselves and the patience of our funding agency, we went to plan B. Every good engineer has a backup plan, and we had an exquisite backup plan. We gave up on polymers, and we turned to those little molecules, the teeny tiny molecules that self-assemble, such as napalm, the example that I gave you for thickening gasoline. Every small molecule that thickens something, whether we're talking about the thickeners for turning oil into the grease in your garage door, as an example, they all have a part that likes the solvent, so they need to have a CO2 philic segment, and then they have to have a CO2 phobic segment that likes to associate. Well, from these previous 6 years, we were experts on things that love CO2. So we knew about CO2 philic things, and CO2 phobic things we took from the industry. These are the ideal things that we would like to have for these small molecule thickeners. Just to give you a ballpark idea, remember we're paying 20 bucks a ton for CO2. So we want to get a thickener that works at about a 0.05 weight percent. That's about 1 pound per ton. If CO2 costs $20 a ton and this thickener costs $5, they'd be willing to pay $25 per ton of thickened CO2 if it was as viscous as we're trying to get it. This is what's really hard. I don't know how many of you have ever made gels with small molecules, but what you typically do is you put the powder in the solvent, and then you have to heat it up to break those bonds and let it dissolve, and then you let it cool to form the gel. It's just like making Jell-O, right? You can't just put the powder in the water and stir it. You have to put it in the boiling water, it breaks all the bonds, you let it cool, it forms a gel. You cannot do that in the oil field. They have these large compressors sending CO2 pipelines all around the field, and there's no way they're going to take that CO2 and put it in a big reactor with an impeller in it, stirring it, heating it, because when you heat CO2 at a constant volume, the pressure goes through the roof. So on top of the difficulty of finding a gelling agent, you have to tailor it so you can just stir it without heating it and have it make a gel. That's really hard, and that's what makes this project another thing that makes it so incredibly difficult. Here's the CO2 loving groups. They're the same groups I showed you on the previous slide. All that we did was we looked in the literature for things that like to associate. We read hundreds, well, I didn't read them, I just looked at the pictures, to be honest with you. We looked at hundreds of papers of molecules that gel things. And we looked at the features of their structures, and these are the chemical groups that like to associate with one another. And what we basically did was we took CO2 philic segments and we matched them up with CO2 phobic associating groups in different architectures. we reviewed the literature, and in this cartoon, the stars represent the sticky part. The straight parts represent rigid CO2 philic groups, like short alkyl chains. And the ones that are a little floppy represent things like silicone oil or polypropylene glycols that are a little bit more flexibility. There's all these different architectures. So what we're doing right now is we're exploring all sorts of small molecules. For instance, take a look at these. CO2 phobic, but they associate. This is a short hydrocarbon chain, so those can be CO2 philic. These things thicken hydrocarbons very easily. In CO2, we found that they were insoluble. When they came out of solution, these did go into solution in CO2, but they didn't change the viscosity. When we vented the CO2, they did self-assemble now that the CO2 was gone and formed fibers. BASF made this molecule to thicken water. It's a carbon. Remember, there's 4 bonds on a carbon, right? One of them goes to a hydrogen. The other 3 go to this group. It has a benzene ring with some functional groups here with polyethylene glycol. These are water-loving arms. This is an amazing water thickener, and you don't have to heat it and cool it. So what we did, we worked with BASF, and we took off these polyethylene glycols, which don't like CO2, and we put in polypropylene glycol, which really likes CO2. And we got this molecule to dissolve. This was CO2 insoluble. We did get this to dissolve in CO2, but it didn't self-assemble and thicken. This is the universal gelator. It's made in Great Britain. They call it universal because this molecule right here gels more liquids than any other molecule that's ever been made. So they nicknamed it the universal gelator. When I spoke with this person, Dr. Knight in Great Britain, and read his papers, maybe this is why his group doesn't have as many papers as they could. They were actually gelling wine and beer. I mean, so I think the graduate students repeated that experiment like 10 times to make sure it worked. But they actually reported gelling wine and gelling beer and different kinds of beers, and then they also did toluene and hexane and things like that. So we made this thing, and it sits like a rock in CO2. So I told him he had to change this to like galactic universe or something. CO2 is not in the universe. It sits there like a rock. These are the associating groups, these 4 hydroxyls. CO2 doesn't have enough solvent strength to dissolve them. We also looked at little molecules. You see this simple little thing here? When I say little, a lot of thickener molecules are teeny tiny, very small. This has primary amines. These react with CO2, and you could form an ammonium carbamate. This is positive, this is negative. These molecules can line up in a row. This is an excellent gelator for some organic solvents, but it's utterly insoluble in CO2. CO2 has a real hard time dissolving ionic groups. So where are we at right now? The polymers, it doesn't look like it's going to happen with polymers. Right now, we are 15 months into a 3-year project to find a small molecule thickener for CO2. We're not there yet. And so we're such good engineers, we actually came up with a plan C. So we have a 3rd plan for this one, and that is to make a thermodynamically unstable 2-phase foam. So just think about it. If you go home to the kitchen sink, you put soap in your kitchen sink and you make these bubbles, this foam, you could sort of consider that to be viscous air. It's like you're scooping up air and holding it in your hand. So you're giving the illusion of it being very viscous. Now it has its disadvantages, right? If you have a foam in a glass of beer, or if you have a foam in your bathtub or a foam in your sink, you have to do some agitation to make it work. So somehow you have to agitate these fluids. And then that foam is going to slowly collapse with time. So this is not as good of a solution as a CO2 thickener. But this is a workable solution. This image here is actually, see this path right here? This is actually a micron scale porous opening through glass slides. And see these bubbles here? These are all bubbles of liquid CO2, and they're separated by dark films of water. So what we're going to try to do is to actually make CO2 foams in the rock. This is an SEM image of actually a thin film of water stabilized by surfactants that had CO2 on one side of it and water, CO2 on both sides of this film and water right there. So what's the idea? Here's the CO2 flood. Remember I told you right now they inject CO2 and they inject water alternately, right? So the idea to make a foam is very simple. You put surfactant in the brine, or you put surfactant in the CO2, or you put it in both phases. And what is your mixer? The mixer is actually the rock. The rock is like a static mixer. So you inject soapy water and CO2, or you can inject brine and soapy CO2, or put soap in both of them and see what happens. For the CO2 soluble surfactants, these are very difficult to identify, but we made great progress in doing it. And here is one example of it. They are typically liquid and non-ionic, and that's good, right? That means at the oil field, they could buy a traditional pump and just pump a liquid surfactant right into the CO2 line and get that to go down into the hole. So typically branched hydrocarbons with a polyethylene glycol head group, and you can get a small amount of solubility in CO2. This is much easier. You all know this, right? It's easy to put soap into water. We have so many household products. There's thousands of surfactants. Now, not every surfactant is a great foaming surfactant. This is the one of the very best. This is the one that we're actually using in a field trial coming up next month in one of the southern states. And this is very soluble in brine, and it goes to the interface, it stabilizes it, the water-loving part points in, this is the water-loving part, the CO2-loving part, which is this part, points out, and you can get some beautiful foams. In both cases, let me remind you, whether it's a CO2-soluble surfactant or a brine-soluble surfactant, both of them must be more soluble in the brine than the CO2. The only way to stabilize a foam is if the surfactant is very soluble in the continuous phase. So this one might start out in the CO2, but once it gets into the rock, it actually partitions or it dissolves into the brine that's already there and makes a foam. How do we test foams? It's actually very easy. It's actually fun. We have a high-pressure windowed cell. We fill it halfway with brine. We fill it halfway with liquid CO2, and we add surfactant, so either the brine or the CO2. We blend it for about 15 minutes with a high-speed impeller at about 2,500 RPM. It forms a beautiful white foam, and then we just watch it collapse. This is the foam. Below it is a clear layer of water that drains out of those films. Above it, as the bubbles start to coalesce, you can get a clear zone of CO2. And eventually, every foam will go back to where you started. What we want to do is get foams that last for hours, days, and weeks. Some foams only last literally for seconds. This is a close-up of what the foam looks like. It's a little hard to see the bubbles, but this is an hour after blending. You get a nice white foam. This is about the size of the bubbles. This is 1 centimeter. Now, after something makes nice foam in these windowed cells, what's really more interesting is whether it makes a foam in a rock. So we do CT imaging. And I believe that's done here as well. This is a medical CT imaging like you may have been in yourself or seen on an episode of House. And this image shows you the high-pressure core holder that's heated and some of the pumps and the tubing leading to it. So what we do is we try to image these foams flowing through a piece of sandstone. Now, in this first example, this is sort of a control. This is a piece of Berea sandstone. You could see right here the bedding planes of the rock going in this direction, these white streaks. So it has some variation in permeability, even in this core, which is 2 inches in diameter and 6 inches long. In our next image, what we did was we made the rock invisible except for these 3 planes to give you a perspective of where the rock is. And we made the CO2 green. The rock is initially filled with brine. So it's a brine-filled rock. We inject CO2, which is green. And take a look at different amounts of pore volume injected. Do you see where the CO2 is flowing? The CO2 is flowing only through those high perm streaks. See these high perm? See how there's layers here? And see how the CO2 is sort of flowing in layers? So that's very poor. This is an illustration of why oil recovery is so low, because it flows through preferentially high permeability paths. This is the same data, just showing you with the images on top of one another. Now what we're going to do is show you what happens when we fill this core with brine, and this time we put some surfactant in the CO2. The CO2 again is green. Do you see the difference this time? This, by the way, is the CO2 distributor at the inlet of the core. You see how the CO2 is pushing like a piston through the core this time? It's not flowing through those little layers again. And this is exactly what you want to have happen. This is giving the illusion that the CO2 is very, very viscous, and it's completely sweeping through this core, getting everything out of it. Here we have another way to image a different set of data where we made the rock completely invisible, and we color-coded the CO2 to be gray. And you see that what it's doing is pushing through here in a piston-like manner, which is exactly what we want. This is an image of where we put the surfactant in the brine that was originally in the core, and then we added pure CO2. This is actually the recipe that we're going to use in the field test in Mississippi. We're going to inject this soapy water first, and then inject CO2 after it. And once again, it's almost like textbook perfect piston-like displacement of CO2. What's the, yeah, that's right, of CO2. The biggest enemy we have here is losing surfactant to the rock surface, adsorption. So this is another example. It's sort of like a textbook example of principles that you learn as an undergraduate that come back to haunt you. In this experiment, we take a core, the same core I showed you, and we start flooding it with the surfactant solution that we're proposing to use. And the concentration we're proposing is 0.25 weight percent. Now, if there was no adsorption of this surfactant going on, then after one pore volume, we would have the concentration coming out as 0.25% the entire time if there was no adsorption. But there is adsorption. So as we start collecting the fluids coming out of the rock, the concentration is close to 0, and then it slowly increases to 0.25. But look at that, 32 pore volumes. We had to put in 32 pore volumes of this solution to get the fluid coming out to have the entering concentration. That's a lot. This number here, you could do a material balance. This is the amount of surfactant that you put in because it's concentration times volume. So the whole rectangle is what you put in. This part shaded here is what came out. This part here, this is what adsorbed. That is a big amount of area. As a result, this is a calculation for the field that we're going to be doing. This is the fluid that we're injecting, 0.25. We're injecting a lot of surfactant, this solution, and here's the distance from the injection well. When we get out to 160 feet, the concentration is going to be essentially 0. In fact, this is the profile right here. If you don't have 0.03 weight percent of that surfactant, you can't make a foam. It's impossible. So there's not going to be any foams here. And these foams here are going to be relatively weak because the concentration is low. And the foams by the wellbore, you see the first 20 feet, they're going to be incredibly strong. So this is the price you pay for adsorption. This is one of the things that really makes it hard to get this technology to work in the field. What's the biggest challenge for these kind of foams? It's high, and this is reminiscent of conditions for some of these aquifers being considered for sequestration. High salinity and high temperature is a killer. Getting foam floods to work is relatively easy at lower temperatures and low total dissolved solids. But as temperature goes up and as solids go up, it's very difficult. So you can either make new surfactants or actually stabilize foams with particles. One of my good acquaintances and somebody who does a lot of work in this area, you're probably familiar with some of his work, Keith Johnston. Keith Johnston is a great individual. He's bright, he's creative, he does a lot of good work in this area. This is one of his recent ideas, is to tailor a surfactant that starts out as non-ionic, but in the presence of a small amount of carbonic acid that forms when CO2 goes into water, it becomes an ionic surfactant. And Keith and his group are specifically trying to get foams to be stabilized up to 120 C. They basically think that these groups here, these little polyethylene glycol groups, sort of shield the ionic nature of this molecule right here, enabling it to stay in solution more than one would expect. Another thing that you could do is that, forget surfactants. You could actually stabilize foams with particles, nanoparticles. It's not commonly done, but you could actually do it. So here in this conceptual diagram, if you have oil and water, if you have tiny nanoparticles, obviously if they're too big, they're just going to sink, right? So you've got to make them really, really small so the gravity force is insignificant. You could tailor them by changing their surface properties by fixing different chemical groups to bond covalently with the surface, and you could use them in place of a surfactant. And these things aren't going to have a propensity to absorb. So they're sort of designed to be injected in the water. So instead of adding surfactant to the water, you actually add nanoparticles to the water. You stir it. If you disperse them right, it's transparent. You can't even see that they're there. And remember what I told you? It has to be, if it's transparent, it'll have a good chance of flowing through the rock. So this is another idea that's being considered right now. So can any of this be applied to sequestration? I don't know. You're probably a better judge of that than me. I am going to tell you one little funny anecdote, though. In 2006, the National Energy Technology Lab actually put out a call for proposals, and I responded to it. And the topic was, how can you add an additive to the CO2 that's being sequestered to improve the sequestration process? That was the topic. CO2-soluble additives to improve CO2 sequestration. So I wrote a brilliant proposal, and I never got eviscerated so badly in my life. I actually thought I was going to get corporal punishment for writing this proposal. Every reviewer said, "Are you out of your mind? I mean, it's bad enough. The economics are bad enough for CO2 sequestration, and you want to add an additive to it. Are you crazy?" And I said to myself, well, then why'd you put out the proposal? I mean, that was the stinking title of the proposal, was to put an additive. And they were good ideas. But boy, did I get spanked on that one. So let me tell you, what possibilities did I talk about today that might be applicable? Well, when you're sequestering CO2, that's CO2 only going down that injection well, right, into the deep saline aquifer. So it has to be CO2 soluble or CO2 dispersible. So if, and I don't know if this is relevant at all, if there is a desire in this aquifer to get a better sweep, because you're going to have fingering, right? This viscosity of CO2 is much less than that of brine. So is viscosity and fingering a problem in sequestration, getting the CO2 to flow in the formation where you want it to? If it is, you can consider CO2 soluble thickeners. Or you can consider CO2 soluble surfactants, right? Because those could go down and generate foams. Or, no one's ever done this one. This is one of my little side projects that I have an undergraduate working on. Can you actually make nanoparticles that you could disperse in CO2 that could stabilize foams? Not dispersing the particles in water, but actually stabilizing nanoparticles in the CO2 to get nanoparticle stabilized foams. I don't know if you're aware of this, but recently a patent came out on CO2 soluble additives for plugging leaks. And this is always a big concern, right? Plugging leaks, potential leaks, slow leaks out of this. So this patent came out, and it's a short patent, and I've written patents before, so I know that it's not like a peer-reviewed paper. They put in a few suggestions. Fluorinone, vanillin. These things I could see going into CO2. They actually listed guar gum. There's enough OH groups here to build a house. That guar gum isn't going to go into CO2. That's the definition of CO2 insolubility. But it's just a patent. I think they put it in there. So I'm not sure something like this would work. During our years, we found out some solids that are extraordinarily CO2 soluble in CO2. Tert-butylated aromatics such as tritert-butylbenzene, tritert-butylphenol, ditert-butylphenols, incredibly CO2 soluble. And sugar acetate, glucose pentaacetate, galactose pentaacetate is actually edible. It's a seasoning. It's a sort of a bitter seasoning for food. So you could even put like edible additives in the CO2. Maybe that'll help the proposal get funded. I don't know. But you know, it's something like, there are indeed a family of compounds when the CO2 depressurizes, the solid will come out. Is that an economically viable thing to consider? Maybe or maybe not. I guess the point I want to make is from our work, we have a whole family of small molecules that are solids that are indeed highly CO2 soluble and could be used for this application. One that's very strange, and you probably never thought of it, I know I never thought of it until I was approached with this problem, is to actually try to find a drag-reducing agent for CO2. So in this country right now, there's 3,100 miles of CO2 pipelines. And if CO2 sequestration ever gets put in place, there's going to be a lot of CO2 pipelines, right? Now, whenever you have fluids flowing through a pipe, there's frictional losses, even for CO2. And periodically on these CO2 pipelines, you have massive compressors that use up massive amounts of electricity. So if you're not familiar with a drag-reducing agent, I have a picture of the Trans-Alaska pipeline system here. Had crude oil. They added a small amount of a polymer, between 10 and 100 ppm of an oil-soluble polymer. What happens, the polymer dissolves everywhere, but the polymer that is dissolved in the oil by the wall dampens the turbulence. And it's not modest. The effect is amazing. You can get 10, 20, 30, 40, 50, 60, 70, 80% friction reduction by adding dilute amounts of polymer. There's hosts of papers on drag-reducing agents for oils. There's dozens of papers on drag-reducing agents for water, but not one for supercritical CO2. Not one. And it wasn't until an operator of one of these pipelines called me and said, we're going out of our minds spending money compressing CO2. So what we're doing is we're taking a look at some of our CO2 thickening agents and adding just tiny amounts of them to the CO2 to see if we can dampen this turbulence along the pipeline to lessen the cost of CO2 transmission. You got to remember, whatever that compound is, you're not getting it back out. There's no way to recover it, so it's going to end up going down the hole, whether it's for EOR or for sequestration. We actually did a test of this. I did a test of a drag-reducing agent at a field this year. We took a polymer in solution, a solvent. I'm sorry, this is recorded now. We took a polymer solution. We pumped it using a pump into a piece of tubing that had multiple little holes drilled into it. We went through a static mixer, and we actually had a beautiful distribution of this polymer in the CO2, and it was a complete failure. But we tried. We didn't get any drag reduction because the molecular weight of our polymer was too low. So where do things look like they're going in the future? CO2 enhanced oil recovery, it is here to stay. It's going to be here for multiple decades. It's going to be here for centuries, in fact. Whether or not CO2 sequestration happens, CO2 EOR is just finding its footing. There's about 135 projects going on right now. Despite that, the thing I wanted to convey to you today is there's a host of ways to improve this process. And the people that run these fields are begging for ideas and solutions, because these problems caused by the low viscosity of CO2, they aren't minor, they are profound. It has a profound negative effect on the performance. So how can you thicken CO2? That would be important. We didn't talk about this today, but layered reservoirs, you folks here have much more geologic experience and expertise than I do. But I think we all know that it isn't just one layer of homogeneous rock. There's these layers. Some of the layers have no oil, but they're so permeable, so much CO2 gets sucked up by them, right? They need chemists and chemical engineers to figure out how to make gels that can go into that layer, form a gel, and stay there. And there are a lot of gels that are formed like that already. They could use better ones, especially for a CO2 environment. How can you make surfactants that work at harsh conditions? How can you stabilize foams with nanoparticles? And I do have several projects in CO2 capture. How can you get CO2 capture? Is it possible to get the price of it to be down more like $40 a ton or $30 a ton? Just something to push it towards the edge of economic attractiveness without any government intervention for enhanced oil recovery operators. And finally, perhaps how to reduce the drag in these pipelines. I want to thank all the people that so patiently funded and supported this work over the years. ARPA-E, the National Energy Technology Laboratory, some older groups that no longer exist under the Department of Energy, the National Science Foundation, some small companies and some large ones. Right now we're receiving a lot of moral support, not any funding, but a lot of moral support from oil companies. They do send us cores, they send us fluids, and to their credit, Denbury has actually given us access to some of their injection wells and some of their pipelines to test some of these ideas. And that's a very significant contribution that they're making to our project. I put John Heller and Cyrus Arani up here. John Heller passed away. He was from New Mexico Tech. I think there is at least one person here that went to New Mexico Tech. Is that right? Any New Mexico Tech alum? One. Well, I don't know if you ever met John Heller. John Heller was one of the first people that I knew when I was very young. I had long, glowing blonde hair. I actually was mistaken commonly for Brad Pitt. I would just do that kind of thing. But when I was really young, John Heller was the first person I met that encouraged young people not to just buy chemicals off the shelf and stick them in the cell and see if it worked, but to actually do molecular design, to tailor things for CO2. He was a pioneer in that area. He was the first one that tried to thicken CO2. Cyrus Arani worked for Gulf and then Chevron. He was the same way. Both of these gentlemen sort of mentored me to do molecular thoughts and molecular design and not just trial and error and just grabbing things and hoping that they work. Thank you for your attention. I appreciate the invitation.
Thank you, Bob, very much for such an informative talk. Now we will have 20 minutes for a Q&A session.
It's really exciting to hear that you're going to field pilot some of these new designs.
Yes.
I was curious, so is that going to be at Citronelle or Cranfield? Is it one of the Denbury properties? And can you tell us a little bit more about the pilot?
Yes, I'll tell you as much as I can.
Okay, yeah,
I can't
understood.
tell you what the field is. Is the tape recording still going here? I don't want to end up with Denbury lawyers after me.
Okay, yeah, well, we can talk about it
But
offline.
I can't tell you this.
Yeah.
I can't tell you this. They have offered us one of their fields. Denbury only does continuous CO2 injection. So we considered for them CO2 soluble surfactants primarily. A lot of their pressures in these fields aren't very high. So they are considering letting us also do surfactant solutions in water also. The portion of the field that they're giving us has horrific gas breakthrough problems. It's hardly producing any oil. So the goal primarily will be just to see the pressure response, and if there's incremental oil, that's nice. But it's going to last 3 months. It's going to start the first week of October.
Yeah. And sort of a side question is whether you've considered any cheap biomolecules, for, these potentially CO2 soluble polymers or even the small molecules, just because bugs are good at producing things with hydrophobic, one side and hydrophilic the other.
My generic answer is I will try at this point any compound that you think might work.
Okay.
But to answer your question more directly, no, we haven't. We have not tested this kind of molecules that you said. We've sort of targeted ourselves to try. When we got our ARPA-E funding, we try to target compounds that will cost no more than $8 a pound.
Yep.
So most of our molecules are based on silicone oils, which are easy to functionalize and inexpensive, and polypropylene glycol. And those are our bases. The fundamental reason we're having real problems is both of those molecules are floppy. They have a lot of flexibility, and they're not good for helping to stabilize these long linear macromolecules. So I think that's one of the things that's hurting us. So any new idea that you might have or share with me, I'd be happy to consider.
Great. Thanks a lot.
Thanks very much. Really enjoyed the talk.
Thank you.
2 questions. You talked about increasing viscosity. What about other properties, for example, density of that foam and how that might affect sweep? That's the first question. The second one, what about degradation in the solubility properties with respect to the oil? I mean,
Yes.
You're dissolving something else maybe to change one property of the CO2. Are you degrading its ability to become miscible in oil?
All right, so I'm so old, I already forgot your first question.
The first one was density, the sweep.
Yes, okay.
Vertical.
So vertical density, I have an extra slide, but I think it would take me too long to find it. Actually, one of the side benefits for changing viscosity is that increasing viscosity has a tremendous increase on slowing the vertical migration. To answer the other part of that first question, we did consider, is there any CO2 density additive? Is there anything that we could add to make the CO2 more dense, right? And the answer is we found a few. In fact, the compounds that make the most profound change on CO2 density are those sugar acetates that I showed. The problem is that you have to add so much of them to make a difference, 10, 15 weight percent. So it would be way beyond the realm of possibility. But Chuck Menke worked with me on exactly that project. He always wanted to make a CO2 densifier. So on your second question, when these, which is the most common question we always get, was what happens to the thickener? So first of all, the advantage of, if we do small molecules, they're going to get sheared in the injection well. The injection rate is so high near the well bore, but the small molecules will be able to just break apart and then come back together. So that's the advantage that they have. Just about every molecule, the polymer, it would have more of a chance of shear degradation near the injection well. With respect to partitioning, just about everything I showed you today, whether it's the big polymers or the little ones, are essentially water insoluble, all of them. And so we're not worried about losing them to the brine. That means that those molecules are going to be lost in one of two places, the oil or to adsorption. And that one, it's hard to answer that accurately or quantitatively, other than to tell you that losses to water will not be the problem. And that's a good environmental problem too, right? We had to clear all these molecules with the EPA. And they wanted us to assure them that we were primarily focusing on water-insoluble problems. And that's indeed the case. So they're going to end up stuck on the rock, perhaps being produced with the oil.
But overall, you'd say it doesn't degrade the CO2's ability to become miscible with oil?
No, the concentrations are so low of these thickeners that would not happen at all.
Any more questions?
Thank you for your presentation.
Thank you.
Very impressive work. So I guess very curious question is, what kind of the permeability or porosity of the rock you would suggest to use that method to use CO2 to drive the through the rock? Because sometimes if the rock is much dense, so probably it's pretty hard to.
So here's something that was beaten into me by the oil companies that I have visited. And I completely agree with it now that I've recovered from my concussion. Everything that I talked to you today is considered by the oil industry as a possible part of a solution. So to answer your question directly, as an example, what I suggest now is that if you have a layered reservoir, and we'll make this easy. Let's say that you have two layers of rock. One has a permeability of 500 millidarcy, and one has a permeability of 50, which are typical values for enhanced oil recovery fields. And let's say there's no oil in the layer that has the high permeability. So when you inject the CO2, 90% of it roughly will go into the top layer and just go out the production well. If you thicken the CO2, that ratio will improve, but you're still going to have most of the CO2 going in that top layer. So what the preferred thing to do is to first mechanically isolate that layer, which is expensive. It costs about $500,000 to do that. And that cost includes injecting a gelling chemical, a solution with a low viscosity. It's water-based. It goes into that layer. It sets up a gel, right? So you block that layer with a gel. Then you inject CO2 plus a thickener into the oil-bearing layer. And so that means that 0% of your CO2 will go into the high perm zone, and all of it in a viscous form will go into the low perm. So basically what I'm saying is there's a suite of tools. The permeabilities from the fields that I'm working with these companies go from roughly, actually 1,000 millidarcies in some of the unconsolidated, loosely consolidated rocks in the southern states, down to about 5 millidarcies in some of the carbonates in West Texas. But they have a suite of tools, infill drilling where they can drill more wells. pressure alterations. You can take the production pumps and change how quickly you produce the fluids. And you could slow down production from offending wells in hopes of diverting fluid away from it. But what they're turning to us for, where they don't have expertise, are these CO2 thickening and CO2 foams. So that's a long answer, but I think I wanted to convey that what I talked about today are, they're like pieces of a puzzle that can solve a bigger problem.
All right, so thank you. The second one is, have you encountered some the problem like preferential pass in the rock? Means, for example, when you inject the CO2, so CO2 going to be select some the preferential path rather
Yes.
than just disperse the
Yes.
sort of the whole system.
So the preferential paths that we are encountering, even in the small amount of fields that I'm gaining access to, are first, very high permeability. That's by far the biggest problem they have. But second, they have natural and some man-made fractures. The foams don't do very well in fractured systems. And the one that's most difficult, that nothing I talked about today works for, are where you actually, in carbonates, you can actually dissolve out these massive flow paths, these vugs and these open voids that you could actually stick your arm in them. And nothing I talked about today works for that. I mean, right now, what they use for those are these preformed particle gels, like a dispersion of small polymer particles. They flow it into those voids, and they swell, just like the polymers in diapers, right? You fill up with liquid, and they sort of block it mechanically. So the CO2 fields, the gel technology is actually doing much better for these CO2 operators than the foams or the thickeners. They're having a great deal of chemical success in employing gels to block these high permeability paths. But what no one has a solution for yet is how to thicken the CO2. That's why it's the project that's sort of nearest and dearest to my heart, is because John Heller started this in 1982. And at one point, there were 14 companies working on this project. And right now, it appears like we're the only idiots left. We're like the Don Quixote of CO2 thickeners. We're just trying and trying. It's gonna either kill us or we're gonna be successful. But that's the one thing that nobody can do that would have the biggest difference.
Thank you very much. Very
You're welcome.
impressive. Thanks.
Thank you.
Thanks very much for the excellent presentation. Concerning the CO2 soluble thickeners and loss in formation, is it primarily adsorption, or do they aggregate also in CO2 and drop out?
My feeling, because we haven't made one that works yet, so I'm going to have to guess, but I think it's going to be a good guess. If you look at surfactants, you know those foaming surfactants I talked about? The ones that absorb the most are the ionic brine-soluble ones, right? And typically you look at, and all of you know this more than I do, but basically, if your formation surface has a negative charge, then you want to use surfactants that have a negative charge, right? And if it's slightly positively charged, then you want to use surfactants with a head group with a slightly positively charged. Those non-ionic surfactants for the CO2 soluble have much lower absorption than the ionics. Every single thickener that I showed you today, with the exception of one, the one that had the primary amines that turn into ammonium carbamates, all of them were non-ionics. And so we do not think adsorption is going to hurt us as much as it hurts the foam project. And as far as will they dissolve in the CO2, well, if they had fluorinated segments, they wouldn't go into the oil. Will they dissolve into the oil? There's a chance that we could lose some dissolving into the oil, but I don't care if that happens. If the CO2 gets to where a lot of oil is, I don't have to keep the CO2 viscous at the leading edge of the CO2. I have to keep the CO2 viscous behind it, so it's pushing it out. So if it loses its viscosity when it mixes with the oil, that's fine. So my gut instinct is we're going to have minor adsorption losses. We could have significant oil losses, but that would be a good problem to have.
Thank you.
Thanks, I really enjoyed your talk.
Thank you.
One thing I was thinking about is the source of CO2 and how from our interest, it'd be really great if you could use, CO2 from power plants. But one of the other major differences in that source of CO2 is that it's not a pure stream of CO2. There are actually some impurities, like SO2, that are present in small amounts.
Yeah.
Do you think there's any way to take advantage of those impurities?
This is an excellent question. This is almost like a planted question. So,
Sorry.
no, that means I can answer it. So in my diagram that I showed you was greatly simplified, right? So first of all, I exaggerated slightly. I have 5 children. I told stories all my life. I often exaggerate, so you'll have to forgive me. When the CO2 comes from these natural sources, it isn't absolutely pure. It'll be 98%. There'll be some water vapor. There might be some methane in it, things like that. But they basically dehydrate it, and there's a few cats and dogs. But where a lot of impurities come from is when the CO2 comes out the production well. Not only is it CO2, but there's H2S, SO2, methane, ethane, propane, butane, pentane. So what happens? Well, Denbury Resources, here's their strategy. I like Denbury because it's sort of like a typical man, like a real tightwad, We're not going to spend money. So they take the gas and they say, we don't care what's in it. Just get a compressor and re-inject it because they want to keep their operating costs low. So they'll re-inject the gas that has methane, H2S, SO2, ethane, propane, butane, all of them. It just goes right in. And I'll tell you what the effect is. Methane and nitrogen are bad. They hurt miscibility. Ethane, propane, butane, SO2, H2S are good because they lower the minimum miscibility pressure. They enhance solubility. Now, another company is called Kinder Morgan, and they're in the Permian Basin. What Kinder Morgan does, they take all the gas from this field, which is massive. It's the largest CO2 flood in the world, and it has all this crap in it. And so they have a little gas processing plant, and they remove the methane, and then in a separate unit, they remove the ethane and propane together, and then they sell a mixed bag of all the natural gas liquids. And so the stream that they return to the reservoir is much higher purity CO2. So most companies, those are 2 of the operators, there's many more operators than those 2. Most companies, at a minimum, they attempt to take most of the methane out, methane and nitrogen, because it hurts miscibility. But those other impurities, even though they're nasty, any sulfur-containing impurity actually enhances miscibility, and so they just leave it in.
So do you think you could come up with, one of these polymers that might react with some of the components that actually reduce the miscibility and
Oh
the
my
reaction
gosh,
causes
were you
something?
like hacking into my computer files? This is how your facility works. That's exactly what we're doing right now. Do you remember I told you that we're having a really, really hard time getting polymers to go into CO2, pure CO2? That's still true, but I haven't given up on it. The reason I still think polymers is the best solution is because they don't need that heating and cooling cycle, right, that gels do. And also, if you make a gel, you know that any gel that you make, if you heat it up too high, it breaks the gel. So you can't use it in high temperature reservoirs. So I still like polymers. I think it's the best solution. And we've recently learned that small amounts of pentane. Now, we're in the lab with undergrads and grad students, right? It's just easier for us to buy pentane as a simulant or an analog of propane, butane, and pentane. We found out that adding a little bit of pentane is enabling us to dissolve some of these polymers significantly. So we're now making a pitch to some of these operators to say, take your CO2 coming out, take out the methane and nitrogen, but instead of selling the ethane, propane, butane, and pentane, leave them all in. Let us use that as a co-solvent to dissolve our polymer, and your polymer, your CO2 will be 20 times more viscous. It'll make more economic sense to do that. So that's exactly what we're doing right now, not as a reactant, as you mentioned, but as a co-solvent.
Thanks.
I will ask a question. So, hydraulic fracturing is currently an area of common broad interest. So, and I know that you have been working on that. So, could you share some perspective on that forefront?
Yes. Forgive me. I should have put in a slide or 2 on this. But when we got funding from ARPA-E If you're familiar with ARPA-E, or if you're not, it's the high-risk part of DOE funding. It's modeled after DARPA, which is the high-risk part of defense funding. So they wanted the craziest ideas possible. So to our knowledge, we're the only ARPA-E funded project on improving traditional petroleum recovery, and we pitched to them by saying, not only can we help enhance oil recovery, but we can help fracking. So CO2 has been used, liquid CO2, and supercritical CO2 has been used to frack wells all the way since the early 1980s. It's still being used today by one company in Texas, but they only do like literally 5 or so CO2 fracks a year. And do you know what the fundamental problem is? The viscosity of CO2 is so low, it cannot transport the proppant sand into the fractures well. In that project, we don't want to just thicken CO2 to like 0.5 centipoise. We want to actually gel CO2, make a beautiful CO2 gel. So that's one area. We're using these same molecules basically at higher concentrations to try to gel CO2 for fracking. And we have a second idea, which is actually, I didn't think of the second idea. It was actually first published in the mid-1980s by Canadian Frackmaster. They proposed using a gel of CO2 bubbles, a foam, just like the foam I showed you, but this time the foam has an oil phase for the continuous phase. So if you have a well that is water sensitive, where the use of water as a hydraulic fluid would cause clays to swell and induce permeability damage, those are called water sensitive formations. We're proposing that perhaps you could frack with a CO2 in oil foam, especially if you're fracking an oil producing layer of shale. And when they did this 30 years ago, when they tried it, you need a surfactant to stabilize a foam, right? There has to be a surfactant to make a foam stable. If you think about it, that surfactant would be half CO2 loving, half oil loving, with both halves hating water. And nobody makes that surfactant. So you can't just buy hundreds of surfactants, which is what they did. They bought dozens of surfactants. Basically, none of them worked. But now we've learned enough where I believe we could easily make surfactants that are CO2 loving on one end, oil loving on the other, blend them in a crude oil, and make a CO2 in oil foam. So that's the two things we're doing on fracking. We're doing gelled CO2 with a direct thickener dissolving it, which I think is really hard to do. I think making CO2 in oil foams would actually be much more realistic to do, even affordably. And you know there are several companies that do CO2 foam fracks now, but they use water-based foams, water or methanol. So we're not trying to compete with those. There's companies that already do that. We're trying to do these truly dry, completely water-free, CO2-based fracking jobs.
Thanks very much. Are there more questions?
I just want to thank everybody again. I know it's a lot of time, and I greatly appreciate it.
Thank you, Bob, very much. So please give Bob another round of applause.
Thank you.
So, thank you very much for coming. And just one thing to mention is that we still have a half an hour time slot available at 4 p.m. to have a one-on-one meeting with Bob. So if you are interested, please let me know. Thank you very much for coming, and have a nice day.
So why is so much left behind? Why is there such a profound amount of oil where we know exactly where it is, but it's still there? Why is such a poor job done by primary and secondary flooding even after all of these years? And that's basically because water and oil don't mix very well. It's not a high-tech explanation, but it's actually very accurate. If you take crude oil and brine, mix them together, you'll get a nice sharp interface between the two of them, and it's just not a very good solvent. It's not really that different from having a lot of oil in your shirt and trying to get it out with water. You're going to leave a lot behind. And the capillary forces retain a great deal of the oil in the small pores of the rock. CO2, on the other hand, is a really good solvent. It's not a perfect solvent, but CO2 is a very good solvent for oil. So let me just take one moment, if you've never seen or aren't familiar with a pressure versus composition diagram, and this is at one temperature, which would be the reservoir pressure. So let's say, just for example, that we have a mixture that's 50-50 of oil, which is on this axis, and CO2 here. And let's say that we're at a pressure corresponding to this value right here. This is a one-phase region. So at those conditions, that's a fair degree of miscibility between the two. In fact, this whole region right here is a single-phase region. This pressure usually is the highest pressure your equipment can go to in the lab. For instance, in my lab, we take these diagrams up to 10,000 psi. Over here, when you get higher proportions of CO2, relatively. All right.
Good morning, everyone. Thanks very much for coming to the Berkeley Lab Earth Sciences Division Distinguished Scientist Seminar. This seminar series is a monthly seminar featuring eminent individuals from various disciplines in the scientific community whose research is outstanding, interdisciplinary, and of broad interest to the strategic interest initiatives in earth sciences. And today it's our great pleasure to have Dr. Bob Enick as our speaker. Bob has been a professor of chemical and petroleum engineering at the University of Pittsburgh since 1985. And he has also been a fellow with NETL since 1987. Bob is an expert in the fields of enhanced oil recovery, geological carbon sequestration, hydraulic fracturing, and high-pressure phase behavior and viscometry. His work has been widely published, and in 2002, he was given the Presidential Green Chemistry Challenge Award, and Bob was also the winner of the 2011 U.S. Secretary of Energy's Achievement Honor Award. Without further ado, please join me to welcome Professor Bob Enick.
Thank you very much. Thank you for the invitation. It's great to be here. Thank you for taking time out of your day to be here. So I'd love to spend in smaller amounts of oil. You have this two-phase liquid-liquid immiscibility gap. So it's not that they're completely miscible, but it's much, much, much more miscible than water. What's really fascinating is even though they're not miscible, in the porous rock they can become miscible. Because what happens is, if you inject CO2, and on this ternary diagram, the injected fluid is here at this part of the triangle, and here we have heavy hydrocarbons and lighter hydrocarbons, and this is a very simplistic model, but it actually represents what happens very well. Your reservoir oil is a mixture of heavy hydrocarbons and lighter hydrocarbons. You may think of this as C1 up to C25 or C30, and this is C30 and higher. So here's the reservoir oil. Here's the CO2 that you're injecting. This diagram is at one temperature and one pressure. So you see that if you mix the two, if the CO2 mixes with the oil, the mixture is somewhere on this line. And there's this huge two-phase region here. So once again, it appears like it's not going to mix. It's going to be immiscible. But what happens is, if you enter, this is like being back in your sophomore year of thermo. If you're in the two-phase region, this is a tie line. This is the CO2-rich phase, and this is the oil-rich phase. And now you see the CO2-rich phase has a slightly different composition. It's not pure CO2 anymore, but it's following this path. And then this mixes with the oil, and the mixture might be on this tie line. And it splits into two phases, and it states, and North America in general has this uncharacteristically large amount of natural CO2. Most of the reservoirs are surprisingly high in purity. Some of them, such as in LaBarge, are very low purity, but utterly massive in the amount. And because of that, there's a great amount of interest of what to do with all that CO2. Well, in the United States, we also have a large amount of crude oil. We've been working fields containing underground layers of sandstone or carbonate for decades, primarily in places like West Texas and in the Permian Basin, where there are several thousand feet below the ground, a great deal of crude oil reserves. And The first way that you try to get this out is by the natural pressure, just from the pressure of the formation and some of the gas that's dissolved in the oil. When you depressurize at the production wells, you get the natural forces to produce it. And then after that, you can inject water into these formations. And this can go on for decades, 10, 20, 30, 40, 50 years of water flooding. But even after all those decades of primary and secondary recovery, usually much more than half the oil remains in place. And here you see a schematic from this company that shows water coming down into this underground layer of sandstone, being injected into an injection well, and proceeding to push and displace the oil towards these 4 production wells around it. Next hour, telling you about the high-pressure world that I live in. It's a good kind of high pressure. Mainly, most of my work deals with CO2 enhanced oil recovery, and perhaps as we go through this talk, you might see some possible applications to the fine work in sequestration that goes on here. So another title that you might envision for this talk, at least the way that I think about it, is this, is what in the world can you do with chemistry and chemical engineering as applied to petroleum engineering? And I found out from being in a department that has both of them that the answer is actually quite a bit. When I first started in my career, there's a lot of people that sort of said, petroleum engineering, that's not a very exciting place or a very challenging place. Chemistry and chemical engineering is a lot more fun, but actually there's a great amount of excellent work that goes on in petroleum engineering, and they can benefit from a lot of chemistry and chemical engineering and physics. And I think the interface between the two is really an exciting place to be working at. You know that when you would drill a well in the United States, most people are hoping to strike a few things, right? You're hoping to strike oil. Here in Pennsylvania, where I'm from, we're in the middle of the Marcellus Shale region, so people are hoping that they have natural gas under there, or you might drill wells for water. But there are a few places in the United States that have not just reservoirs of natural CO2, but prolific reservoirs of natural CO2. In fact, in the world, United